In this video, we will explain how to use the Laplace transform to solve differential equations. We already proved this property, which I mentioned that it was the most important property for the Laplace transform. It says that the Laplace transform of the derivative of a function is equal to s times the Laplace transform of the function minus the function evaluated at 0. And we're going to see that this is very useful to solve a differential equation. Let's suppose that we have, let's do an example. Let's suppose that we have this differential equation, dy dt plus 4 times y equal to 6 times e to the 2t. And let's suppose that we have that y of 0 is equal to 3. Okay, then what we can do, we are looking for a function y of t that satisfies the property. Then what we can do is we can apply the Laplace transform on the left and the Laplace transform of the right. When we apply the Laplace transform of the left, we know that the Laplace transform of the derivative of a function is s times the Laplace transform of the function minus y of 0. But in this case, y of 0 is equal to 3. It will be minus 3. And since the Laplace transform is linear, then this is just plus 4 times the Laplace transform of y, and then equal to the Laplace transform of this. But let me remind you this property. We know that the Laplace transform of e to the at is 1 over s minus a. This means that the Laplace transform of this function would be 6 times 1 over s minus, in this case a is 2, then minus 2. Notice that once you apply the Laplace transform, essentially all the t's disappear and you only have s. This is an s, the Laplace transform is a function in terms of s, everything is a function in terms of s. The next step is to solve for the Laplace transform of y. I would like to think that you can see this like s times an apple minus 3 plus 4 times an apple equals 6 over s minus 2. Can we solve for an apple? Then we can solve for an apple like s plus 4 times an apple equal to 3 plus 6 over s minus 2. And then we can solve by dividing by this. But let's just, this is I think a good analogy, but let's just work with the Laplace transform of y, and let's do it like this without the apple. Then in this case we can combine these two, and we have that s plus 4 times the Laplace transform of y minus 3 equal to 6 over s minus 2, and therefore we have that the Laplace transform of y is equal to, let's say, still times s plus 4 is equal to 3 plus 6 over s minus 2. What is 6 plus 3 plus 6 s minus 2? This is 3 times s minus 2 over s minus 2 plus 6 over s minus 2, and this will be 3 s minus 6 plus 6 over s minus 2, and this is just 3s over s minus 2. That means that when I divide by s of s plus 4, I get that the Laplace transform of y is equal to 3s over s minus 2 times s plus 4. Okay, this is usually what is going to happen. We have a differential equation in terms of t. We apply the Laplace transform on both sides of the equation. Then we solve for the Laplace transform of y, and we end up with the Laplace transform of y equal to an expression in terms of s. And essentially what we need to do is we need to compute the Laplace transform inverse of this. Then we need to find a function f of t such that the Laplace transform of f of t is equal to this. But then when you compare this with this, you will get that y is equal to the f of t. But then this is the third step, and it may be the more challenging, how to compute the Laplace transform inverse of this. But this is an example that we did earlier, or we did something similar. Notice that we're going to be using this formula, but this expression doesn't look like something like the right hand side of this formula like that. But what is going to help us? Partial fractions. We can do partial fraction here. We can write this as a over s minus 2 plus b over s plus 4, and then this is equal to a times s plus 4 plus b times s minus 2 over s minus 2 times s plus 4. And then we can compare this numerator. Where do I write? Let me erase this part here, this part here, this part here, and then we can compare this numerator 3s with as plus 4a plus bs minus 2b. Then we compare coefficient. What is the coefficient of s on the left? It's 3. And what is the coefficient of s on the right? Here we have these two, a plus b. What is the constant coefficient on the left? There is no constant coefficient. There is no factor term without a s. Then we have a 0. And what is the constant coefficient on the right? Is 4a minus 2b. Okay, then we solve this system of equations. We can multiply by 2 and add. When we multiply by 2 and add, what do we get? We get 6 equal to 6a, and that means that a is equal 1. And if a is equal 1, using this equation here, we get that b is equal to, okay, 4 minus, yes. Then we get this. That means that this expression, notice that essentially what we did is we did a rewriting. Instead of writing it like this, we can see it like 1 over s minus 2 plus 2 over s plus 4. And now we can use this formula. This is the Laplace transform. This is the Laplace transform of e to the 2t. And this part is the Laplace transform of 2 times e to the negative 4t. That means that the solution of this differential equation is y equal to e to the 2t plus 2 times e to the negative 4t. Okay, then we have used the Laplace transform to solve this differential equation. You don't have to do this, but let me just show you that indeed this is a solution. What is this initial condition? What happened when I replace t by 0? What do I get? E to the 0 plus 2 times e to the 0, which is 3. Then this is true. Now let's take the derivative of this, which is the solution, and let's check that it satisfies the differential equation. What is the derivative of this function? It is 2 times e to the 2t minus 8 times e to the negative 4t, right? And then this is the derivative, let's see, plus 4 times the function. The function is e to the 2t plus 2 e to the negative 4t. Let's see what this is equal to. It's supposed to be equal to this. Let's see if it is true. What can I combine? I can combine this with this times this, and I get 6 times e to the 2t, and you see that this part, and when you multiply this by this, it cancels out. Then in D, we have checked that that this function satisfies this differential equation with this initial condition, and we have done that by using the Laplace transform. I think that I would like to stop here. This is it.